For centuries, astronomers and scientists believed they had a solid understanding of our home galaxy, the Milky Way. We thought we knew its size, its shape, and its structure based on our observations of stars, gas, and cosmic dust that make up the galaxy. The Milky Way was long thought to be a relatively flat spiral galaxy with a well-defined structure, rotating slowly but steadily in the vast cosmos. But recent revelations have shattered these long-held assumptions. Astronomers, armed with more advanced technology and deeper insights into the workings of the universe, have made a startling discovery that has left the scientific community reeling. The Milky Way is not what we thought it was, and its true nature may be far more complex than we ever imagined. The Milky Way, which has been the subject of countless studies and observations, has always seemed like a familiar object in the sky. Its spiral shape, with sweeping arms of stars and gas surrounding a dense central bulge, appeared to be the model for most spiral galaxies in the universe. We've long believed that our solar system sits within one of these arms, revolving around the galactic center in a predictable orbit. But this new discovery upends everything we thought we knew about the structure of the Milky Way. New data and observations have revealed that the Milky Way is not simply a neat, flat disk, but a far more dynamic, complex, and chaotic system, challenging the very foundations of galactic science. One of the key discoveries that sparked this new understanding of our galaxy is the revelation that the Milky Way's shape is far more warped than we initially believed. Previous models depicted the Milky Way as a flat, spiraling disk with neatly organized arms extending out from a central bulge. But astronomers, using more sophisticated methods, have now determined that the galaxy's disk is not flat, but instead displays significant warping. The galaxy's shape, it turns out, is far more distorted, with its arms bending and twisting in ways that were previously unknown. This discovery, which comes from examining the positions of distant stars and gas clouds, suggests that the Milky Way is far more dynamic than we ever imagined. The cause of this warping, it seems, lies in the galaxy's gravitational interactions with other nearby galaxies, particularly the Andromeda Galaxy. Our two galaxies, which are on a collision course with each other, have been influencing one another's shape for billions of years. The gravitational pull from Andromeda has been warping the outer regions of the Milky Way, causing the galaxy's disk to bend in dramatic ways. This process, known as tidal interaction, is a common phenomenon in the universe and is responsible for the distorted shapes of many galaxies. It was always suspected that the Milky Way's shape could have been influenced by external forces, but it wasn't until recently that astronomers were able to confirm this theory through more detailed observations. However, the warping of the Milky Way's disk is not the only surprising discovery to come from the recent findings. Astronomers have also uncovered evidence that the Milky Way is much larger than previously thought. For decades, estimates of the galaxy's size were based on the assumption that the galaxy's outermost regions were neatly confined to its spiral arms. But new observations, using advanced instruments and more precise measurements, have revealed that the Milky Way's outer regions stretch far beyond what we had originally believed. The galaxy's true extent is likely many times larger than previously thought, with stars and gas clouds extending into a vast halo of material that was once thought to be a separate, unrelated structure. This discovery has major implications for our understanding of the Milky Way's role in the broader universe. We've long believed that the Milky Way was just one of billions of similar galaxies scattered throughout the universe. But if the Milky Way is much larger than we realized, it could indicate that our galaxy plays a more dominant role in the cosmic landscape than previously thought. The size of a galaxy is often closely tied to its gravitational influence, and a larger Milky Way could mean that it has a stronger gravitational pull affecting the motion and behavior of nearby galaxies, including Andromeda. This new understanding of the Milky Way's size could reshape our view of its relationship with neighboring galaxies and its influence on the local cosmic environment. In addition to its size and warping, the Milky Way has also proven to be more complicated in its structure than we ever imagined. The galaxy's spiral arms, once thought to be neatly organized, are actually far more chaotic, with stars and gas clouds moving in unpredictable ways. This chaotic movement, which has been uncovered by recent observations of the galaxy's outer regions, suggests that the Milky Way is not a simple, stable system, but one that is constantly evolving and changing. While the spiral arms are still present, they are not as rigid and defined as we once thought. Instead, they are dynamic and constantly shifting, with new stars being born and older stars being ejected or moving toward the galaxy's center. This dynamic behavior of the Milky Way challenges our previous understanding of galaxies. We've always thought of galaxies as relatively stable systems, with stars and gas organized into distinct patterns and structures. But the discovery that the Milky Way is more chaotic and less organized than we realized suggests that galaxies may not be as predictable as we once thought. This new understanding opens up exciting possibilities for future studies of other galaxies and their behaviors. It also raises new questions about the processes that govern the formation, evolution, and behavior of galaxies on a cosmic scale. At the heart of this revelation is the realization that the Milky Way is not just a static, unchanging entity. It is an active, dynamic system, constantly evolving and interacting with other galaxies, stars, and cosmic forces. The discoveries made by astronomers in recent years show that the Milky Way is not the simple, well-understood structure we once thought it was, but a far more complex, dynamic, and evolving entity. And this realization has profound implications for how we understand not only our own galaxy, but the entire universe itself. For one, the new discoveries suggest that galaxies may undergo more dramatic changes over time than we previously thought. The Milky Way's ongoing interactions with Andromeda, for example, could result in significant changes in the galaxy's structure and behavior in the coming billions of years. These interactions could lead to the merger of the two galaxies, creating a new, larger galaxy with a completely different structure and dynamics. This discovery challenges the idea that galaxies are stable, unchanging objects, and suggests that they are in a constant state of flux, evolving and reshaping over time. Additionally, the Milky Way's chaotic movement and dynamic nature point to the possibility that other galaxies may be similarly complex and unpredictable. For years, astronomers have believed that galaxies follow a predictable pattern of growth and evolution, with distinct phases of star formation and interaction. However, the recent findings about the Milky Way suggest that this may not be the case at all. Instead, galaxies may be far more diverse and variable in their behavior than we ever realized, and understanding their evolution may require a more nuanced, flexible approach. As we continue to study the Milky Way and other galaxies, we will likely uncover even more unexpected discoveries. Our understanding of galactic structure, dynamics, and evolution is rapidly evolving, and the future holds exciting possibilities for new insights and revelations. The Milky Way, once thought to be a familiar, well-understood object, is now revealed to be a far more complex and mysterious entity with a history and future that is still unfolding. As we look toward the future of galactic research, we can expect the unexpected, more discoveries that will challenge our assumptions and transform our understanding of the cosmos. As astronomers continue to analyze the newly discovered complexities of the Milky Way, one of the most significant revelations has been the realization that our galaxy's structure is much more intricate and dynamic than we once believed. For years, we understood the Milky Way as a classic barred spiral galaxy, one with sweeping arms of stars and gas, a central bulge, and a relatively uniform disk of material. However, the latest discoveries suggest that the Milky Way is far more unusual and active than this simplified model implies. These new insights are reshaping how we view not only our own galaxy, but also the evolution of galaxies in the broader universe. The first indication that the Milky Way is far more complicated than we thought came from detailed observations of its outer regions. Astronomers, using new techniques like precise measurements of star movement and data from the European Space Agency's Gaia mission, have discovered that the outer disk of the Milky Way is not flat and smooth, but instead exhibits significant warping. The galaxy's arms, once thought to be rigid structures formed from dense regions of stars and gas, now appear much more malleable. These arms are not the neat, perfect spiral formations we once envisioned. Instead, they are more irregular, twisting and bending in unexpected ways. This revelation upends our understanding of the Milky Way's basic structure and forces us to reconsider how it evolved over time. One of the key factors in this discovery is the galaxy's dynamic movement, influenced not only by gravity, but by cosmic interactions with neighboring galaxies. The Milky Way's interactions with its closest galactic neighbor, the Andromeda Galaxy, are particularly significant. These two galaxies are on a collision course set to merge in about 4.5 billion years. While this event is still far in the future, the gravitational pull between the Milky Way and Andromeda is already affecting their shapes. The gravitational forces between the two galaxies are beginning to warp the outer disk of the Milky Way, causing the spiral arms to stretch and twist in ways that were previously unnoticed. This interaction is likely responsible for the irregularities and distortions that have been observed in the Milky Way's outer regions. This discovery forces us to rethink our view of galaxy evolution. For decades, we have believed that galaxies grow and evolve in a relatively stable, predictable manner. Galaxies, we assumed, followed a simple life cycle, from the formation of stars and gas clouds to the formation of distinct spiral arms and stellar clusters. But the evidence now suggests that this process is far from simple. Galaxies are not static structures. They are dynamic systems that are constantly interacting with each other, influenced by a variety of cosmic forces. The Milky Way's interaction with Andromeda, for instance, is just one example of how galaxies can influence each other's evolution. This raises a fundamental question. Are all galaxies as dynamic and complex as the Milky Way, or are there different types of galaxy evolution yet to be discovered? The idea that galaxies, including our own, are shaped by external forces challenges the traditional model of galaxy formation, which suggested that galaxies form from the collapse of gas clouds under their own gravity. Instead, we now know that galaxies grow through an ongoing process of cosmic interactions. These interactions, whether between neighboring galaxies, dark matter halos, or gravitational waves, play a critical role in shaping the final structure of a galaxy. In the case of the Milky Way, its spiral arms, bulge, and disk have all been influenced by external forces over billions of years. These forces have left an imprint on the galaxy, giving it the distinctive structure we see today. But what does this mean for the future of the Milky Way? As it continues to interact with Andromeda and other galaxies in the local group, the shape and structure of the Milky Way will continue to evolve. The upcoming collision between the Milky Way and Andromeda will be a transformative event, likely causing both galaxies to merge into a new, larger galaxy. During this process, the Milky Way's spiral structure will be lost, replaced by a more elliptical shape. The stars and gas in the two galaxies will redistribute, creating new regions of star formation. While this event will occur far in the future, it highlights the dynamic and constantly changing nature of galaxies. Far from being fixed objects, galaxies are living, breathing entities that undergo continuous transformation. But beyond the merging of galaxies, other cosmic phenomena are at play that could further shape the Milky Way's future. Supermassive black holes, which exist at the centers of most galaxies, play a crucial role in regulating galaxy growth. The Milky Way's own supermassive black hole, Sagittarius A, has been influencing the behavior of stars and gas in its vicinity for billions of years. While Sagittarius A is relatively quiet at the moment, it has the potential to become active again, potentially affecting the galaxy's evolution. As material falls into the black hole, it can release vast amounts of energy, affecting the surrounding gas and stars and influencing the growth of new structures. In addition to black holes, the influence of dark matter on the Milky Way's structure is another critical factor. Dark matter, the invisible substance that makes up most of the galaxy's mass, exerts a gravitational force that shapes the galaxy's overall structure. While dark matter cannot be directly observed, its presence is inferred from its effects on visible matter. It is believed that dark matter forms a massive halo around the Milky Way, helping to keep the galaxy together and influencing the motion of stars and gas within the galaxy. This dark matter halo may also play a key role in the Milky Way's interactions with neighboring galaxies, including Andromeda. As dark matter is key to the structure and stability of galaxies, any changes in its distribution could have a profound effect on the evolution of the Milky Way. Another important aspect of the Milky Way's future is its role in the larger cosmic network of galaxies. The Milky Way is part of the Local Group, a collection of galaxies that includes Andromeda, the Triangulum galaxy, and several smaller galaxies. The interactions within this group will shape the future of each galaxy, but the influence of other, more distant galaxies will also play a role. Galaxies throughout the universe are constantly interacting through gravitational forces, and the Milky Way is no exception. As the universe expands, the Milky Way will continue to move and evolve, influenced by both nearby and distant galaxies. These cosmic interactions are a reminder that our galaxy is not an isolated object, but a part of a much larger interconnected system of galaxies. Despite these fascinating insights, we are still in the early stages of understanding the true nature of the Milky Way. The discoveries of the last few years have challenged many of our previous assumptions, but they have also opened up new avenues of research. How do these external forces, like interactions with neighboring galaxies and the influence of dark matter, affect the Milky Way's growth? What can we learn from other galaxies in the universe that could shed light on the Milky Way's past, present, and future? What we do know is that the Milky Way is not the simple, unchanging galaxy we once thought it was. It is a dynamic, evolving system shaped by a variety of cosmic forces. These discoveries challenge the traditional view of galaxies as fixed, predictable objects and suggest that the universe is far more complex and interconnected than we had imagined. As we continue to study the Milky Way and its interactions with other galaxies, we are likely to uncover even more surprising insights about the nature of our home galaxy and the universe at large. The Milky Way, once thought to be a well-understood object, is proving to be far more mysterious, far more dynamic, and far more essential to the understanding of the cosmos than we ever realized. As our understanding of the Milky Way evolves, it becomes increasingly clear that our galaxy's complexities extend far beyond its structure and shape. The more we learn about its dynamic movements, the way it interacts with other galaxies, and the hidden forces at work, the more we realize that the Milky Way is not just one of billions of similar galaxies. It is a truly unique cosmic entity with a story that may hold the key to unlocking the mysteries of galaxy formation, evolution, and even the larger workings of the universe itself. One of the most intriguing aspects of the Milky Way's newfound complexity is the realization that its core is far more volatile and dynamic than we ever imagined. For years, astronomers have observed the center of the Milky Way as a somewhat static, though somewhat active region. It was known to contain a supermassive black hole, Sagittarius AB, whose immense gravitational pull affects the surrounding stars and gas. However, recent discoveries have shown that this region is far more tumultuous and energetic than previously believed. Far from being a passive gravitational well, the core of the Milky Way is now thought to be a dynamic environment in which stars are born, destroyed, and influenced by complex interactions within the galactic center. At the heart of this new understanding lies the behavior of Sagittarius A, the supermassive black hole at the center of the Milky Way. For many years, this black hole was believed to be relatively quiescent, emitting only faint radiation as it slowly consumed nearby gas and stars. But recent observations have revealed that Sagittarius A is far more active than previously thought. Using data from the Event Horizon Telescope, Astronomers have captured more detailed images and measurements of the black hole, revealing powerful jets of radiation being ejected from its poles. These jets are not only a sign of the black hole's immense power, but they also affect the surrounding gas and stars, causing turbulence in the galactic center. This newfound activity in the Milky Way's core is part of a larger pattern of galactic activity. Supermassive black holes are thought to play a crucial role in the evolution of galaxies, and Sagittarius A is no exception. The energy and material being expelled from the black hole's jets affect the surrounding environment, influencing the formation of new stars, the movement of gas, and the behavior of other celestial objects. These jets also play a critical role in regulating the amount of gas available to form new stars. The more active the black hole, the less gas there is to fuel star formation, which can result in periods of dormancy in the galaxy's stellar activity. This interaction between the black hole and the galaxy's star formation process is just one example of how the Milky Way's core plays a much more dynamic role in shaping the galaxy than previously realized. But the Milky Way's complexity doesn't end with Sagittarius A. In addition to the supermassive black hole, the galaxy's core is home to a variety of other phenomena that were once overlooked or misunderstood. For example, astronomers have recently discovered that the galactic center is rich in a wide variety of exotic stars and cosmic objects, such as neutron stars, white dwarfs, and stellar remnants that are scattered throughout the region. Many of these objects are the remnants of stars that have gone through their life cycles, either dying in supernovae or collapsing into black holes. Some of these objects have been ejected from the core of the galaxy, creating a chaotic environment where stars, gas, and dark matter interact in unexpected ways. This chaotic activity has major implications for our understanding of the Milky Way's overall behavior. Galaxies, as we once understood them, were thought to be relatively stable systems with stars moving in predictable orbits around a central point. However, the complexity of the Milky Way's center suggests that galaxies may be far more dynamic than we previously thought. Instead of being stable, passive systems, galaxies are active, evolving environments in which stars and other cosmic objects interact and evolve over time. The interactions between these objects, whether through gravitational forces, radiation, or material exchange, create a galaxy that is far more complex than just a static arrangement of stars. Beyond the galactic center, new discoveries have also revealed that the Milky Way's outer regions are far more complicated than we once believed. The previously assumed simple, flat spiral structure of the Milky Way has been replaced with a more dynamic picture, one in which the galaxy's spiral arms are more irregular, warped, and constantly shifting. These new observations suggest that the Milky Way is influenced by external factors beyond its immediate environment. For example, the Milky Way is on a collision course with its neighboring galaxy, Andromeda, and this impending merger will likely have a profound effect on the galaxy's structure. The collision of these two massive galaxies will cause their stars and gas to interact, triggering bursts of star formation and potentially even leading to the creation of new black holes. The collision will also have a dramatic effect on the Milky Way's spiral arms, potentially causing them to lose their distinct shape. This potential collision with Andromeda is just one of many examples of how the Milky Way's dynamics are shaped by external forces. It's not just the internal processes of the galaxy, such as the influence of Sagittarius A, or the interaction between stars and gas, that govern its behavior. The Milky Way is also influenced by its interactions with other galaxies, clusters, and cosmic structures. These interactions, over billions of years, have shaped the Milky Way's evolution and will continue to shape it in the future. The more we learn about these interactions, the more we realize how interconnected galaxies are, each one influencing and being influenced by the others. As astronomers continue to probe deeper into the mysteries of the Milky Way, we are beginning to see how these external forces and interactions play a key role in shaping the evolution of our galaxy. Far from being a solitary object, the Milky Way is a part of a vast and interconnected network of galaxies, each influencing the others in subtle but profound ways. The Milky Way's place in this network is crucial to understanding its future evolution. Whether it's the impending collision with Andromeda or the gravitational influence of distant galaxies, the Milky Way is far more integrated into the fabric of the universe than we previously realized. Perhaps most surprisingly, the more we learn about the Milky Way, the more we realize how little we truly know about it. While we have long considered our galaxy to be one of the most well-understood cosmic entities, these new discoveries are forcing us to reevaluate our assumptions. The Milky Way is far more complicated, dynamic, and interconnected than we ever imagined. And as our observational tools and models continue to improve, we are sure to uncover even more surprises. The journey into understanding the Milky Way is far from over, and with each new discovery, we come one step closer to truly understanding the forces that shape our home in the universe. As we continue to unravel the mysteries of the Milky Way, one of the most intriguing aspects of this galaxy is its dynamic nature, not just in terms of its internal structure and evolution, but also in how it interacts with its environment on a much larger scale. The Milky Way, it turns out, is not just a solitary galaxy moving through the void. It is part of a much larger cosmic network of galaxies, all interconnected in ways that were previously underappreciated. These galaxies form clusters, and even more intriguing, superclusters, vast regions of the universe in which galaxies are bound together by gravity. The Milky Way is no exception. It is a member of the Local Group, a small cluster of galaxies that also includes the Andromeda Galaxy, the Triangulum Galaxy, and a number of smaller satellite galaxies. This group of galaxies is part of an even larger cosmic web that stretches across the universe, connecting galaxy clusters in a vast, intricate structure. But the Milky Way's place in this network is not just a passive one. Our galaxy is actively interacting with its neighbors, and these interactions are influencing its evolution in profound ways. The most immediate example of this is the impending collision with the Andromeda Galaxy, a future event that will reshape the Milky Way in ways we cannot yet fully comprehend. For many years, astronomers had considered the Milky Way and Andromeda to be relatively isolated from one another. However, new data has shown that these two galaxies are on a collision course, and the event is expected to occur in about 4.5 billion years. When this collision happens, it will not be a simple merging of two galaxies. The gravitational forces at play will cause massive disruption. Stars will be scattered, gas clouds will collide and compress, and new stars will be born in the chaos. These interactions will also likely lead to the formation of a supermassive black hole at the center of the newly merged galaxy, as the black holes at the centers of both the Milky Way and Andromeda collide and combine. Though this collision will not result in stars directly colliding with one another, as the distances between individual stars are vast, the overall structure of the Milky Way will be radically altered. The spiral arms will likely be disturbed, and the galaxy may lose its familiar shape, transitioning into a more elliptical form. This transformation will mark the end of the Milky Way as we know it, and signal the beginning of a new era in its history. What's more fascinating is that the influence of Andromeda's gravitational forces is already affecting the Milky Way. The two galaxies are drawing closer to each other, and their gravitational pull is already distorting the Milky Way's shape. The outer regions of the Milky Way's disk are being warped, and some of its stars are being tugged toward Andromeda's. Gravity. This interaction, though subtle now, will intensify as the galaxies approach each other. The coming collision could be one of the most significant events in the Milky Way's history, completely altering its structure, star formation rates, and cosmic composition. But the Milky Way's interactions aren't limited to Andromeda alone. Our galaxy is also part of the larger Local Group, which contains several smaller galaxies that orbit around it. These satellite galaxies are not only gravitationally bound to the Milky Way, but they also influence its evolution. One of the most interesting interactions is with the Magellanic Clouds, two irregular galaxies that orbit the Milky Way. These galaxies, though much smaller, are interacting with the Milky Way in fascinating ways. As the Magellanic Clouds orbit the Milky Way, they pass through its outskirts, disrupting the galaxy's outer regions. The gravitational pull of the Milky Way is slowly pulling these smaller galaxies inward, eventually merging them with the Milky Way in a process that could take billions of years. As these satellite galaxies spiral inward, they will bring with them gas and stars, contributing to the growth of the Milky Way. These mergers, over time, have played a significant role in the evolution of the Milky Way, enriching it with new material and adding to the galaxy's stellar population. The ongoing process of galactic interactions highlights a key aspect of our galaxy's evolution. Galaxies are not isolated, independent systems, but dynamic, interconnected entities. The Milky Way, like all galaxies, is constantly changing due to the gravitational interactions it has with other galaxies, stars, and cosmic structures. These interactions can trigger new waves of star formation, influence the distribution of gas and dust, and even lead to the formation of new black holes and other exotic cosmic objects. This is an important realization, as it suggests that the Milky Way has not always been the familiar structure we see today. It has been shaped and influenced by a multitude of cosmic forces, from the early collisions that formed its spiral structure to the ongoing interactions with neighboring galaxies. The future of the Milky Way is similarly dependent on these interactions. The galaxy's eventual collision with Andromeda will mark a major turning point in its history, but it will also contribute to the larger cosmic cycle of birth, death, and rebirth that characterizes the evolution of galaxies. Understanding the Milky Way's place in the larger cosmic landscape is essential for understanding how galaxies evolve over time. Galaxies do not exist in isolation. They are part of a vast interconnected web of cosmic structures that interact, collide, and merge. The Milky Way's evolution is deeply influenced by its interactions with neighboring galaxies, dark matter, and cosmic forces. These interactions will continue to shape the Milky Way's future, driving its growth, its star formation, and its eventual transformation into a new cosmic entity after its merger with Andromeda. This broader perspective of galactic evolution challenges the traditional view of galaxies as static objects. The Milky Way, once thought to be a relatively stable, isolated system, is now revealed to be part of a dynamic, constantly evolving network of galaxies. Its future is not predetermined, but is shaped by the ongoing interactions with its neighbors. This realization opens up exciting new possibilities for our understanding of the universe. As we continue to study the Milky Way and other galaxies, we will likely uncover more about how galaxies interact, evolve, and transform, shedding light on the processes that govern the cosmos at the largest scales. The future of the Milky Way is still uncertain, but one thing is clear. It will continue to evolve and change, influenced by the forces that govern the universe. Whether it's through the gravitational pull of nearby galaxies, the influence of dark matter, or the birth of new stars, the Milky Way will remain a dynamic, evolving entity. As we continue to study the galaxy's interactions and structure, we will undoubtedly uncover more secrets about its past, present, and future, secrets that will shape our understanding of the universe for years to come. As we dig deeper into the mysteries surrounding the Milky Way, we begin to see how its complexity extends beyond mere structural anomalies and interactions with neighboring galaxies. The discovery that our galaxy is far more dynamic than we once thought brings to light a host of questions about the forces driving its evolution. The Milky Way's role in the larger cosmic landscape is not just about its collisions and interactions with Andromeda or other nearby galaxies. It's about the unseen forces and processes that shape its stars, gas, dark matter, and other components. These forces are constantly at work, influencing everything from the galaxy's stellar population to its expansion rate and even its eventual fate. One of the key factors influencing the evolution of the Milky Way is the role of dark matter. While we cannot see dark matter directly, we can observe its gravitational effects on visible matter. Dark matter is thought to make up the majority of the galaxy's mass, and its presence is responsible for the way the Milky Way behaves on a large scale. Without dark matter, the galaxy would not have the mass necessary to hold its structure together. The gravitational pull of dark matter helps keep the galaxy intact, preventing it from flying apart as its stars and gas move through space. But dark matter's role in shaping the galaxy goes beyond just holding it together. It also plays a key part in the formation of stars, the creation of black holes, and the growth of galaxies. One of the most fascinating aspects of dark matter is its influence on the Milky Way's rotation. The galaxy's outer regions, where the influence of visible matter is weaker, still rotate at speeds far higher than we would expect, based on the visible mass alone. This discrepancy between the visible and invisible matter in the galaxy's outer regions has been a key indicator that dark matter is present. The gravitational pull of dark matter in the galaxy's halo accounts for the faster-than-expected rotation in the outer disk. In a sense, dark matter is not just an invisible force, it is a driving factor behind the Milky Way's motion and structure. Recent studies have also revealed that the Milky Way's dark matter halo is more complicated than we once thought. Instead of being a smooth, spherical structure, the dark matter in our galaxy is thought to be spread out in a more irregular, clumpy pattern. This clumping may be responsible for some of the galaxy's unexpected behaviors, from the warping of its spiral arms to the irregularities in its rotation. The discovery that dark matter is not evenly distributed within the Milky Way is reshaping how we understand the galaxy's overall structure. These irregularities could also influence how the Milky Way interacts with other galaxies and cosmic objects. The distribution of dark matter in the galaxy's halo may play a critical role in how it grows, how it forms stars, and how it eventually merges with neighboring galaxies like Andromeda. But the role of dark matter in the Milky Way is just one piece of the puzzle. We must also consider the behavior of ordinary matter, gas, stars, and dust, that makes up the visible portion of the galaxy. While dark matter provides the framework that holds the Milky Way together, it is the ordinary matter that makes up the galaxy's visible structure. The distribution of gas and stars in the Milky Way is not random. It is heavily influenced by the galaxy's internal dynamics, including the gravitational pull of dark matter and the interactions between different components of the galaxy. Recent observations have shown that the distribution of gas in the Milky Way is more complex than previously thought. Instead of being evenly spread across the galaxy's disk, gas is concentrated in specific regions, often in the form of massive clouds that are in various stages of collapse and star formation. These gas clouds are the birthplaces of new stars, and their distribution throughout the galaxy plays a key role in the ongoing process of stellar evolution. Some of these gas clouds are located in the galaxy's spiral arms, while others are scattered more irregularly throughout the outer regions of the galaxy. This non-uniform distribution of gas suggests that the Milky Way is not simply a static system. Rather, it is a galaxy in constant motion, with gas clouds drifting through its disk, forming stars and being affected by the gravitational pull of dark matter and the Milky Way's central supermassive black hole. The ongoing cycle of star formation, from the collapse of gas clouds to the ignition of new stars, plays a crucial role in shaping the galaxy's evolution. As stars are born, they enrich the surrounding gas with heavier elements, further contributing to the galaxy's complex chemical composition. This process also regulates the rate of star formation, as the death of massive stars and supernovae releases energy that can either trigger new rounds of star formation or halt it altogether. The Milky Way's star formation activity is not uniform either. In some regions, such as the spiral arms, stars are forming at a rapid pace, creating new generations of stars and enriching the surrounding gas. In other regions, star formation has slowed or even stopped, creating quieter, less active regions. These variations in star formation are influenced by a variety of factors, from the amount of gas available to the region's position within the galaxy. But one of the most important factors in determining where stars form is the gravitational influence of the galaxy's supermassive black hole. At the center of the Milky Way lies Sagittarius A, a supermassive black hole with a mass millions of times that of our Sun. This black hole exerts an enormous gravitational pull on the surrounding stars and gas. While this gravitational force does not directly affect the formation of stars in the galaxy's outer regions, it does play a key role in the galaxy's overall behavior. The material that falls into the black hole, whether in the form of gas, dust, or even entire stars, can release immense amounts of energy, which influences the surrounding gas and stars. This energy can either trigger new star formation or suppress it, depending on the nature of the interaction. The influence of Sagittarius A is not just confined to the central region of the galaxy. Its gravitational pull extends throughout the Milky Way, subtly affecting the movement of stars and gas in the outer regions. This complex interplay between the black hole, dark matter, gas clouds, and stars is what gives the Milky Way its dynamic, ever-changing nature. It is a galaxy in motion, constantly evolving and adapting to the forces at work within it. As we continue to study the Milky Way, it becomes increasingly clear that our understanding of its structure and behavior is far from complete. New observations and discoveries are constantly reshaping our view of this familiar yet enigmatic galaxy. From the complex distribution of dark matter to the irregular movement of stars and gas, the Milky Way is revealing itself to be a far more dynamic and active system than we ever imagined. And as we continue to probe its mysteries, we are sure to uncover even more unexpected revelations about its true nature and the forces that drive its evolution. The Milky Way is not just the galaxy we call home. It is a living, breathing cosmic entity, constantly changing, adapting, and interacting with the larger universe around it. As we continue to explore this extraordinary galaxy, we are gaining new insights into the very nature of galactic evolution and the role the Milky Way plays in the broader cosmic landscape. What we once thought was a familiar, stable system is now revealed to be a complex, dynamic, and ever-changing entity, shaped by forces beyond our current understanding. As we continue our investigation into the unexpected complexities of the Milky Way, it becomes clear that one of the most significant factors influencing the galaxy's structure and behavior is the interplay between its gas, stars, and dark matter. For decades, astronomers have tried to model the Milky Way's mass distribution and determine its gravitational influence on the surrounding environment. However, recent discoveries have revealed that the traditional models of the Milky Way's mass, based primarily on visible matter, are insufficient. The true mass of the galaxy is far greater than what was previously thought, and much of it resides in the form of invisible dark matter. Dark matter, a mysterious substance that cannot be detected by conventional means, accounts for roughly 85% of the galaxy's total mass. Though we can't observe dark matter directly, its presence is inferred from its gravitational effects on visible matter, such as stars and gas. The dark matter in the Milky Way forms a massive halo around the galaxy, extending far beyond its visible disk. This dark matter halo helps to hold the galaxy together, preventing it from flying apart under the force of its own rotation. It is also responsible for the unexpected motions of stars at the outer edges of the galaxy, which rotate much faster than would be expected given the visible mass alone. The discovery that dark matter makes up such a large portion of the Milky Way's mass has had profound implications for our understanding of the galaxy's structure. For years, astronomers assumed that the galaxy's mass was predominantly composed of the visible stars and gas that make up its disk and spiral arms. But with the realization that dark matter plays such a crucial role, scientists have had to revise their models of the Milky Way's rotation and mass distribution. In fact, the influence of dark matter extends far beyond the visible parts of the galaxy, with its gravitational pull affecting the motion of stars in the outer regions of the Milky Way. This new understanding of the Milky Way's mass and structure is not only reshaping how we think about our galaxy, but is also providing valuable insights into the broader nature of galaxies themselves. The role of dark matter in holding galaxies together is not unique to the Milky Way. It is thought to be a fundamental feature of all galaxies. In fact, the presence of dark matter is likely the reason why galaxies, regardless of their size or type, maintain their structure and do not collapse under the force of their own gravity. Understanding dark matter and its role in galactic dynamics is essential to understanding how galaxies form, evolve, and interact with each other. But dark matter's influence on the Milky Way is not limited to its gravitational pull. Recent studies have also suggested that dark matter may play a more direct role in the galaxy's evolution. While dark matter does not interact with light or other forms of electromagnetic radiation, it does interact with itself through gravity, and some theories suggest that it may have a more active role in shaping the distribution of stars and gas in galaxies. In particular, dark matter is thought to influence the formation of galactic structures, such as the spiral arms of the Milky Way, by guiding the flow of gas and stars. This dynamic interaction between dark matter and visible matter is responsible for the complex structure of galaxies like the Milky Way. The gravitational pull of dark matter has shaped the galaxy's spiral arms, its central bulge, and its overall disk structure. It has also influenced the rate of star formation in the galaxy. Dark matter's gravitational influence can trigger the collapse of gas clouds, leading to the formation of new stars. In this way, dark matter plays a critical role in the ongoing evolution of galaxies, influencing their growth and shaping their structure over billions of years. Beyond the galaxy itself, the discovery of dark matter's influence on the Milky Way has also opened up new avenues of research into the larger structure of the universe. The Milky Way is part of a vast cosmic network of galaxies, and the interactions between these galaxies are governed by the gravitational pull of dark matter. The Milky Way's place within this network is crucial for understanding the larger forces that shape the universe. The interactions between galaxies, such as the Milky Way's impending collision with Andromeda, are influenced by the distribution of dark matter in the universe. In fact, the movement of galaxies through space is largely governed by the gravitational effects of dark matter, which forms vast cosmic structures known as dark matter halos that extend far beyond the visible galaxies. The discovery of dark matter's pervasive influence on the Milky Way and other galaxies has also raised important questions about the very nature of the universe itself. What is dark matter, and how does it work? While we have known of its existence for decades, scientists still have no direct explanation for what dark matter is made of. It does not interact with light or electromagnetic radiation, making it invisible to traditional telescopes. Some scientists speculate that dark matter may be made up of exotic particles, while others propose that it could be a form of matter that interacts with gravity in ways that are not yet fully understood. The role of dark matter in shaping the Milky Way is just one example of how the study of galaxies is leading us to new and unexpected discoveries about the universe. The more we learn about the Milky Way's structure, mass, and evolution, the more we realize how little we truly understand about the universe as a whole. The Milky Way, once thought to be a simple spiral galaxy, is revealed to be a much more complex and dynamic system, shaped by the invisible forces of dark matter and influenced by the interactions with neighboring galaxies. As astronomers continue to probe the mysteries of our galaxy, they are uncovering insights that challenge our understanding of space, time, and the fundamental forces that govern the cosmos. Understanding the true nature of the Milky Way is not just about understanding our galaxy. It is also about understanding the larger structure of the universe. The discoveries about the Milky Way's dark matter halo, its complex rotation, and its interaction with neighboring galaxies are just the beginning. As we continue to explore the galaxy and the larger cosmic network it inhabits, we will undoubtedly uncover even more surprising revelations that will change the way we think about the universe and our place in it. The Milky Way is no longer just the familiar galaxy we call home. It is a dynamic, evolving system that is shaped by both visible and invisible forces, from dark matter to gravitational interactions with nearby galaxies. As we continue to study its past, present, and future, we are learning not only about our galaxy, but also about the very nature of the universe itself. The Milky Way's journey is just one piece of a much larger cosmic puzzle, and as we uncover the secrets of our home galaxy, we move one step closer to understanding the mysteries of the cosmos. As our understanding of the Milky Way deepens, it becomes increasingly clear that its history and future are far more entwined with the universe than we previously imagined. The Milky Way is not just another galaxy. It is a crucial player in the larger cosmic drama, its evolution shaped by forces far beyond our immediate neighborhood. One of the most exciting aspects of this understanding is the Milky Way's role in the broader cosmic structure known as the cosmic web. The cosmic web is a vast interconnected network of galaxies, clusters, and dark matter that stretches across the entire universe. It is a structure so large that it can be difficult to fathom. Billions of galaxies, like the Milky Way, are woven together by dark matter filaments that span unimaginable distances. The Milky Way is a member of this cosmic web, part of a group of galaxies bound together by gravity, and it is influenced by the larger movements and interactions within this web. The idea of the Milky Way as part of the cosmic web challenges our previous assumptions about the isolation of galaxies. For years, we viewed galaxies as individual, isolated entities, each evolving on its own. However, the realization that galaxies are interconnected through a network of dark matter and gravitational forces has profound implications for how we understand the Milky Way's role in the universe. The Milky Way, it turns out, is far from isolated. It is part of a much larger cosmic structure, and its evolution is deeply influenced by the forces at play within this vast network. One of the most significant revelations to come from this new understanding of the Milky Way's place in the cosmic web is the discovery of large-scale galactic flows. For years, astronomers believed that galaxies were distributed relatively evenly throughout the universe. But new observations have shown that galaxies are not spread out in a uniform fashion. Instead, they are arranged in a series of massive cosmic filaments bound together by dark matter and gravity. These filaments form a kind of cosmic web, with galaxies strung along the threads like pearls on a necklace. The Milky Way is situated in one of these cosmic filaments, part of a larger network of galaxies that are gravitationally bound to one another. The local group, which includes the Milky Way, Andromeda, and several smaller galaxies, is part of a much larger supercluster of galaxies known as the Laniakea supercluster. This supercluster is just one of many in the cosmic web, and its movement through space is influenced by the gravitational pull of other superclusters. The Milky Way, along with its neighbors, is being pulled toward the Great Attractor, a mysterious concentration of mass located at the center of the Laniakea supercluster. This massive object is drawing galaxies toward it, causing a large-scale flow of galaxies toward this gravitational well. This large-scale flow of galaxies has major implications for the future of the Milky Way. While our galaxy is not on a direct collision course with the Great Attractor itself, it is moving toward the region where it is located. Over billions of years, this gravitational pull will likely affect the motion of galaxies within the Laniakea supercluster, including the Milky Way. But the Milky Way is not just influenced by the Great Attractor. Its movement through the cosmic web is also being shaped by the larger-scale forces of dark matter and cosmic gravity, which exert an unseen influence on the behavior of galaxies and galaxy clusters. This new understanding of the Milky Way's position in the cosmic web raises an important question. How will the galaxy continue to evolve over the next billions of years? While we know that the Milky Way is on a collision course with Andromeda, the larger-scale movements within the cosmic web will also influence the galaxy's future. The gravitational pull from other galaxies and superclusters could shape the Milky Way's future evolution, potentially triggering new waves of star formation or altering the galaxy's structure. This dynamic interplay between the Milky Way and its larger environment suggests that galaxies are not static objects, but rather part of a constantly evolving cosmic dance. Beyond the gravitational pull from other galaxies and the influence of dark matter, the Milky Way is also influenced by the presence of cosmic voids, vast regions of space that are nearly empty of galaxies and matter. These voids are a natural part of the cosmic web, and the Milky Way, like all galaxies, is located on the edge of one such void. These voids, while seemingly empty, play a crucial role in shaping the structure of the universe. Their existence helps to create the large-scale distribution of galaxies, as the galaxies are drawn toward the denser regions of the cosmic web while avoiding the emptier voids. This interplay between dense regions and cosmic voids is an essential part of the Milky Way's place in the larger universe. The discovery of the Milky Way's connection to the cosmic web and its interactions with neighboring galaxies, superclusters, and cosmic voids represents a dramatic shift in our understanding of galactic evolution. For years, we thought of the Milky Way as a self-contained system, isolated in its corner of the universe. However, we are now realizing that our galaxy is part of a much larger and more interconnected cosmic structure. The Milky Way, like all galaxies, is shaped by its place in the cosmic web, and its evolution is influenced by the complex interactions that take place on a cosmic scale. This understanding of the Milky Way's connection to the cosmic web has profound implications for our understanding of the larger universe. Galaxies are not isolated islands in the vast sea of space. They are part of an intricate, interwoven structure that shapes their evolution. The discovery of this larger cosmic web opens up new avenues for exploring how galaxies form, interact, and evolve. It suggests that the universe is far more interconnected than we once thought, with galaxies influencing each other in ways that are still being uncovered. As we continue to study the Milky Way's place in the cosmic web, we are likely to discover even more surprising insights into the universe's large-scale structure. This understanding not only reshapes our view of the Milky Way, but also provides us with a new lens through which to explore the cosmos. The Milky Way, once thought to be just another spiral galaxy, is now revealed to be a dynamic, evolving entity, influenced by the larger forces of the universe. Its future, shaped by gravitational interactions with other galaxies, the influence of dark matter, and the movements within the cosmic web, is still unfolding. And it is a story that will continue to surprise and astonish us for years to come. The more we learn about the Milky Way and its interaction with the larger cosmos, the clearer it becomes that our galaxy's fate is intimately tied to the forces governing not just its immediate neighborhood, but the entire universe. As we venture deeper into this understanding, we are confronted with the realization that the future of the Milky Way, and even our own solar system, is far from a static, predictable process. The Milky Way's future is shaped by a dynamic interplay of forces: gravitational, dark energy, galactic collisions, and cosmic evolution, forces that are constantly in motion, pushing our galaxy toward a new chapter in its history. Perhaps the most significant of these impending forces is the collision between the Milky Way and its closest galactic neighbor, the Andromeda Galaxy. For years, astronomers have known that the Milky Way and Andromeda are on a collision course, but only recently have we come to understand the scale of this future event. The two galaxies are expected to collide and merge in about 4.5 billion years, a cosmic event that will mark the end of one era and the beginning of another. While this might seem like an event far beyond human reach, its implications are monumental, not just for the Milky Way, but for the future of the entire local group of galaxies, including Andromeda. The collision between these two massive galaxies will be one of the most dramatic events in the universe's history. Galaxies, as we've come to understand, are not just isolated collections of stars, gas, and dust. They are dynamic systems with a variety of internal components, and when two galaxies collide, these components interact in fascinating and sometimes violent ways. As the Milky Way and Andromeda collide, their spiral arms will merge, their stars will be reshuffled, and the two galaxies will combine to form a new, larger galaxy. This process will trigger massive bursts of star formation as the gas clouds within the galaxies collide and compress. New stars will be born, while old stars may be ejected or displaced as the gravitational forces of the merging galaxies wreak havoc. However, despite the dramatic nature of this collision, one surprising aspect of this galactic merger is that stars themselves are unlikely to collide. The distances between individual stars are so vast that even during a galactic collision, the chances of stars physically colliding with each other are incredibly low. Instead, the most noticeable effects of the merger will be the reshaping of the galaxy's structure. The Milky Way and Andromeda will likely lose their distinct spiral arm features and will evolve into a more elliptical galaxy over time. The merging of the two galaxies will create a new galaxy with a different star distribution, potentially altering the dynamics of star formation and the overall energy balance of the new galaxy. This galactic merger is not just a local event, it will have far-reaching consequences. The gravitational interactions between the Milky Way and Andromeda will affect neighboring galaxies in the local group. As the two largest galaxies in the group merge, they will disturb the orbits of smaller galaxies, potentially causing them to be flung out of the group or to be pulled into the larger galaxies. This will reshape the local group and could lead to the formation of new galaxy clusters. The effects of this merger will ripple throughout the surrounding space, influencing the gravitational dynamics of galaxies on much larger scales. Beyond the immediate impact of the merger itself, the collision will also trigger the formation of new supermassive black holes. Both the Milky Way and Andromeda contain supermassive black holes at their centers. As these two black holes merge during the collision, they will form an even larger black hole at the center of the newly merged galaxy. This process will release an enormous amount of energy, known as gravitational radiation, which will be detectable even across vast cosmic distances. The newly formed supermassive black hole will play a central role in the evolution of the new galaxy, influencing the formation of stars, the behavior of gas clouds, and the dynamics of the galaxy's growth. While the merger between the Milky Way and Andromeda will reshape the galaxy's structure, it is also a significant event in the larger context of cosmic evolution. This galactic collision is just one example of the ongoing process of galaxy formation and evolution in the universe. Galaxies are not static. They are constantly interacting, merging, and evolving over billions of years. In fact, the Milky Way and Andromeda are not the only galaxies on a collision course. Numerous other galaxies in the universe are also on paths that will eventually bring them together. The study of these collisions provides valuable insights into the processes that drive galaxy evolution, helping us to understand how galaxies form, grow, and change over time. The eventual merger of the Milky Way and Andromeda is a reminder that galaxies, though seemingly eternal, are subject to the same forces of cosmic change as everything else in the universe. The vast distances between stars and galaxies may make these changes appear slow and imperceptible in our lifetimes, but in the context of the cosmos, they are part of a continuous dynamic process. The Milky Way, once thought to be a stable and predictable system, is revealed to be part of a much larger, ever-evolving cosmic structure, a structure that will continue to change and evolve long after we are gone. As we continue to study the Milky Way and its interactions with Andromeda and other galaxies, we are uncovering more about the forces that govern the formation and evolution of galaxies. We are learning how galaxies grow, how they interact with one another, and how they eventually merge into new, more complex structures. This knowledge is essential not only for understanding the Milky Way's future, but for understanding the larger processes that shape the universe itself. One of the most profound implications of the Milky Way-Andromeda merger is the potential for new star formation. When galaxies collide, the gas clouds within them are compressed, triggering bursts of star formation. This process, known as starburst, leads to the creation of new stars at a much higher rate than we see in galaxies today. These new stars, born from the gas clouds of the merging galaxies, will play a crucial role in the future evolution of the Milky Way and Andromeda's merger. These stars will provide the energy and material necessary for the next generation of cosmic structures, creating the conditions for future planetary systems and, possibly, new life in the distant future. But the merger will not be the end of the story. As the two galaxies merge and evolve into a new entity, the Milky Way and Andromeda will continue to evolve, subject to the forces of dark matter, gravity, and cosmic expansion. The new galaxy formed from this collision will continue to grow, absorbing neighboring galaxies, forming new stars, and undergoing the cycle of life and death that has defined galaxies throughout cosmic history. The Milky Way, once a solitary spiral galaxy, will live on as part of a larger, more dynamic cosmic entity, a testament to the ongoing process of galactic evolution. As we continue to explore the Milky Way's past and future, one of the most fascinating aspects of our galaxy is the long-term evolutionary process that will take place as it merges with Andromeda. Though this event is billions of years away, understanding its implications allows us to explore the far future of our galaxy and the universe as a whole. This merger will be a monumental shift, not just for the Milky Way and Andromeda, but for the entire cosmic landscape, setting the stage for new cosmic entities to form, new stars to burn, and possibly even new forms of life to emerge. But beyond the merger itself, this chapter of the Milky Way's history will lead to an entirely new phase in galactic and universal evolution. One of the immediate effects of the galactic collision will be the redistribution of the stars and gas that make up the Milky Way and Andromeda. While stars will rarely collide directly due to the vast distances between them, the gas clouds in both galaxies will be compressed and shocked during the merger, leading to a massive burst of star formation. This period of heightened star production, known as a starburst, will transform the combined galaxy, creating vast new clusters of young hot stars that will illuminate the new galactic structure. The stellar birth rate during this phase will be far greater than anything observed in either galaxy today, as the gas clouds, now compressed and agitated by the collision, collapse into new stars. This stellar explosion will fuel the creation of new stellar nurseries, where clusters of stars are born in an energetic frenzy. In the aftermath of this stellar explosion, the newly formed stars will begin to disperse into the newly merged galaxy. Some of these stars will travel along the galaxy's newly warped spiral arms, while others will be drawn toward the newly formed central black hole. The center of the merged galaxy will be dominated by an enormous supermassive black hole, created from the merger of the black holes at the center of the Milky Way and Andromeda. This black hole, possibly tens of billions of times the mass of the Sun, will exert an immense gravitational pull on the surrounding stars, gas, and dust, shaping the evolution of the galaxy for billions of years to come. This new, supermassive black hole will play a crucial role in shaping the future of the galaxy. It will continue to grow as it consumes surrounding material, possibly triggering new bursts of star formation as it feeds. In addition, the black hole's gravitational influence will affect the motion of stars within the galaxy, altering their orbits and causing the galaxy to evolve in complex ways. The formation of this black hole will also mark the beginning of a new era for the galaxy, one that could lead to the development of new cosmic structures such as quasars, highly energetic objects powered by the accretion of matter onto a black hole. But the merger of the Milky Way and Andromeda will also have broader consequences for the surrounding environment. The two galaxies are not isolated objects. They are part of a larger network of galaxies in the local group, and their collision will influence the fate of other galaxies in the group. The gravitational interactions between the Milky Way and Andromeda have already begun to pull smaller galaxies, such as the Magellanic Clouds, into the gravitational influence of the two giants. These smaller galaxies will be absorbed into the newly merged galaxy, contributing their stars, gas, and dark matter to the new system. The absorption of these smaller galaxies will continue over billions of years, reshaping the local group and expanding the boundaries of the Milky Way's influence. The merger will also affect the surrounding regions of space. The gravitational pull of the combined Milky Way-Andromeda system will disrupt the motion of neighboring galaxies, potentially altering the course of galaxies that lie within the local group. Some galaxies may be drawn into the merged galaxy's orbit, while others may be flung out into intergalactic space. The interactions between galaxies in the local group will continue to reshape the group's structure, with the Milky Way and Andromeda at the center of this transformation. This process of galactic merging and disruption is not unique to the local group. It is part of a larger cosmic process in which galaxies interact, collide, and evolve over cosmic timescales. However, it's not just the immediate galactic interactions that will shape the future of the Milky Way and Andromeda. The broader forces of the universe, particularly the expansion of space itself, will also play a crucial role in the long-term evolution of our galaxy. As the universe continues to expand, the galaxies within it are moving away from each other, driven by the force of dark energy. While this expansion has little effect on galaxies that are gravitationally bound to each other, it will influence galaxies that lie at greater distances. In the far future, galaxies that are not part of the local group will continue to recede from the Milky Way and Andromeda, further isolating our galaxy within the larger cosmic landscape. As the Milky Way and Andromeda merge, their interactions will create a new cosmic entity, one that will likely have a completely different structure from the galaxies we see today. The resulting galaxy could be a large elliptical galaxy with a more spherical shape than the current disk-like structure of the Milky Way. This elliptical galaxy will be home to an even larger population of stars, many of which will have been born during the starburst period following the merger. The galaxy will continue to evolve, with new stars forming from the gas clouds left behind by the collision, while older stars are gradually displaced toward the galaxy's outskirts. This new galaxy will also have profound implications for the future of our solar system. While the merger of the Milky Way and Andromeda will not directly cause the destruction of our solar system, it will likely result in significant changes in the environment surrounding it. The gravitational interactions between stars, gas, and dark matter could shift the orbits of stars in our galaxy, possibly bringing our solar system closer to or farther from the galaxy's center. The changes in the local environment could also affect the likelihood of future star formation and the development of new planetary systems. While our solar system may survive the merger, the broader cosmic changes resulting from the merger could alter the conditions for life in the galaxy in ways that are difficult to predict. Looking even further into the future, the Milky Way-Andromeda merger marks the beginning of a new era in galactic evolution, an era in which galaxies continue to merge and evolve, driven by the gravitational forces at play in the universe. The process of galaxy formation and evolution will continue, with galaxies growing larger, more complex, and more diverse over billions of years. The Milky Way's transformation into a new, merged galaxy will be a defining moment in this process, but it is only one part of a much larger cosmic story. As we reach the final chapter of our journey into the Milky Way's unexpected transformation, it becomes clear that our galaxy's story is far from over. The discoveries of the last few years have revealed that the Milky Way is not the simple, static structure we once thought it was. Far from being a predictable, well-understood system, it is a dynamic, evolving entity, influenced by countless forces, many of which are still being uncovered. The future of the Milky Way is uncertain, but it is undoubtedly one of cosmic change, shaped by the ongoing interactions with neighboring galaxies, the influence of dark matter, and the larger cosmic forces that govern the universe. The collision and eventual merger with the Andromeda Galaxy, while still billions of years away, will mark one of the most dramatic moments in the Milky Way's history. It will change the structure of our galaxy, the behavior of its stars, and even the dynamics of its black hole. However, this transformation is only one aspect of the larger evolution of galaxies in the universe. The Milky Way's future will be shaped not only by its collision with Andromeda, but also by the ongoing cosmic forces at play in the universe. One of the key forces that will shape the future of the Milky Way is dark energy, the mysterious force that is causing the accelerated expansion of the universe. While this force is still not fully understood, it is clear that dark energy will have profound implications for the future of galaxies. As the universe expands, galaxies are moving away from each other, and this expansion is being driven by dark energy. However, this expansion has little effect on galaxies that are gravitationally bound to each other, such as the Milky Way and Andromeda. The two galaxies will continue to collide and merge, creating a new galactic entity in the process. But for galaxies outside the local group, dark energy is pushing them farther away, leading to a cosmic isolation that will shape the future of those galaxies and their interactions with the Milky Way. In the distant future, the Milky Way and Andromeda will no longer be the dominant forces in the local universe. As the galaxies in the local group merge and evolve, the gravitational influence of other galaxies will become more pronounced. The Milky Way's role in the larger cosmic landscape will be reshaped by its interactions with other galaxies and galaxy clusters. The future of our galaxy will be defined not only by its collision with Andromeda, but also by the ever-expanding cosmic web in which galaxies are continually interacting and evolving, each one shaping the other's destiny. As the Milky Way evolves, so too will the stars and planetary systems within it. The future of our own solar system, while still uncertain, is deeply tied to the fate of the Milky Way. As the galaxy's structure changes, the position of our solar system will also be influenced by the larger cosmic forces at work. The gravitational interactions between stars, gas, and dark matter could alter the orbit of our solar system, either bringing it closer to the galactic center or pushing it farther into the outskirts of the galaxy. These changes will not only affect the solar system's environment, but could also alter the conditions necessary for life. The most immediate consequence of the Milky Way's transformation will be the creation of new stars. During the merger with Andromeda, gas clouds will be compressed, triggering massive bursts of star formation. This period of intense star formation will give rise to a new generation of stars, some of which may eventually form planets capable of supporting life. The birth of new stars in the wake of the galactic merger will create new solar systems, each with its own set of unique characteristics. But, as new stars form, old ones will die. Some will explode in supernovae, enriching the surrounding gas with heavier elements, while others will collapse into black holes. The cycle of star birth and death will continue, with each generation of stars leaving its mark on the galaxy. However, this process of star formation and evolution will not last forever. Over billions of years, the rate of star formation in the Milky Way will gradually slow down. As the galaxy's gas clouds are consumed in the process of star formation, there will be less material available to create new stars. Eventually, the Milky Way will run out of gas and the star formation process will cease. The galaxy will enter a period of stellar dormancy, where only old stars remain. Over time, these stars will burn out, leaving behind a galaxy filled with stellar remnants, white dwarfs, neutron stars, and black holes. The once vibrant, active galaxy will become a quiet, aging system, its star formation activity reduced to a trickle. As the Milky Way's evolution slows down, its relationship with the larger universe will continue to evolve. The expansion of the universe, driven by dark energy, will continue to push galaxies farther apart. The Milky Way's neighbors will move away, and the local group will eventually become isolated from the rest of the cosmos. The once thriving galaxy cluster will become a quiet, isolated group of galaxies, surrounded by an ever-expanding void. The Milky Way's fate, once shaped by cosmic interactions, will gradually be determined by its own internal dynamics and the ongoing influence of dark energy. In the farthest reaches of time, the Milky Way, like all galaxies, will eventually face its final fate. The exact timeline of this process is still unclear, but current theories suggest that billions of years from now, the galaxy will reach a point of no return. As the galaxy's stars burn out and its gas is exhausted, it will gradually fade into a state of dormancy, a silent remnant of its once glorious past. The supermassive black hole at the galaxy's center will continue to grow, consuming any remaining material until the Milky Way becomes a faint shadow of its former self. But even in this distant future, the Milky Way's story is not over. The remnants of the galaxy, along with the black holes, neutron stars, and other cosmic remnants left behind, will continue to exist for an unimaginable amount of time. Though the Milky Way may fade into quiet solitude, its legacy will live on in the cosmic fabric of the universe. Its influence will continue to shape the future of galaxies, stars, and the larger cosmic structure. In the end, The Milky Way's journey will be just one chapter in the vast unfolding history of the universe. Its transformation from a vibrant, dynamic galaxy to a quiet, fading relic is a reflection of the larger processes that govern the cosmos. As galaxies continue to evolve, collide, and merge, the Milky Way's story will be woven into the fabric of the universe's ongoing evolution, a testament to the forces that shape all cosmic entities, from the smallest stars to the largest galaxy clusters.